Hi, my name is Yuri, and I want to tell you today about a paper that is published in the International Conference on Software Engineering in 2024 called Automated Program Repair, What is it good for? Not Absolutely Nothing. This is joint work with Khadil, Claire, and myself. I want to talk today about automated program repair, which is a technology that has come out of the software engineering research community that in many measures has been an unmitigated success. Given a program, some passing tests and some failing tests, automatic program repair automatically edits the source code to produce a program that passes all the tests. So this actually works, and over the past 15 years, there have been hundreds of techniques produced that have attempted to produce patches for different kinds of bugs in different kinds of languages, and have worked on trying to improve the quality of the produced patches. So it doesn't produce a patch always, and when it produces a patch, it's not always correct, but surprisingly often it does in fact produce a patch. Now, in our community, the way you really measure success is not through papers or awards, but instead whether industry is using your work. And in fact, automatic program repair has been used in industry quite a bit. It's used today at Facebook and at Bloomberg, at several other companies. And the way that it is used in industry is the following. So bugs can be detected, and a tool can generate a patch completely automatically. Those two green boxes you see at the top are completely automated. But then from there, the process takes on a much less automated approach. In particular, a human then reviews the generated patch, and then a human can decide to edit the patch, and they make the ultimate decision as to whether or not to submit the patch. And once they do that, the patch undergoes a standard review process that companies follow, which typically involves even more humans. So what's going on here? Why is it that this inherently automated process is being used in this manual way? Well, in one study at Meta, developers used one of these tools, SAPFix, that's being used internally, and they found that only 48% of the produced patches are actually correct. So the others produce a patch that looks correct, it passes all the tests, but in fact it does not fix the underlying bug. And then, of the patches that they deemed correct, for half of them they still chose to edit them, presumably to improve something about those patches. So again, what's happening here? Why is this inherently automated process being used in this very manual way? Well, we've actually known for a very long time that automatically produced patches can overfit. The way that these automatic program repair tools work is that they're given some partial specification of correctness. So typically it is a set of tests, and they try to produce a patch that passes all the tests. So it fits to this partial specification. But in fact, it's possible to produce a patch that satisfies all the tests, but it fails to generalize to the underlying specification that the developers actually wanted. In particular, what that means is that there exists some more tests that the developers didn't write that the patch would in fact be failing. And in fact, a recent review article on automatic program repair found that the grand challenge in today's research on automatic program repair is this problem of weak specification, and in particular the problem that automatic program repair can generate patches that overfit to the test and don't generalize to the intended specification. There's been lots of work to try to reduce overfitting and try to produce patches that are of higher quality. But fundamentally, the way that automatic program repair is being used today in industry is through this manual process. So there are automatically produced patches that are made available to developers. And we don't know the answer to the question of, does the availability of automatically produced patches help developers debug? Now, there was a study performed 10 years ago that looked at this question in the realm of very early automatic program repair tools, but this was done before we had a better understanding of overfitting and automatic program repair, and before we had the modern notions of measuring quality of patches. And there's been several pieces of work that have looked at related questions like looking at what happens when developers get multiple patches to consider, and what happens when developers are asked to trust automatic program repair, what factors make them trust or not trust these kinds of tools. And in fact, as early as 2006, people were proposing that patches can actually be better bug reports than bug reports themselves. And so there's been lots of questions that have been answered kind of on the periphery here, but fundamentally, given today's modern automatic program repair tools and our understanding of overfitting, we do not know the answer to the question of whether the availability of automatically produced patches help developers debug. And it is our goal with this work to try to shed some light onto this question. So how do we do that? We designed a user study with 40 participants who were students at the University of Massachusetts. They had a median of 6 years of programming experience. And we had these 40 participants use 3 modern automatic program repair tools, Recoder, T-Bar, and Symfix, and these are intended to come from different types of automatic program repair. And they used 9 real-world defects, all picked from Defects for J benchmark, and we used all these artifacts to create 30-minute debugging tasks. So we created 4 different treatment groups. First, we had the control group, and in the control group, the participants saw the source code, which contained a bug, and they saw some tests, most of which passed, but some of which failed, and they were asked to fix the bug. And then we had 3 experimental groups, and in all 3 of these experimental groups, the developers also saw the source code, and then they also saw the tests, but then they also saw a code suggestion, and the code suggestion made all the tests pass. And the developers did not know whether the code suggestion was human written or automatically generated, and whether it fundamentally fixed the underlying bug or not. They just knew that it made all the tests pass. And so there were 3 different types of code suggestions they actually saw. They could have gotten a developer-written correct suggestion, so this is correct as judged by the developers of the project. It's written by a human, and it actually fixes the underlying bug. They could have gotten an automatically program-generated, again, correct suggestion, so something that makes all the tests pass and fixes the underlying bug. Or they could have gotten an automatically program-generated deceptive suggestion. So a deceptive suggestion makes all the tests pass, but it does not, in fact, fix the underlying bug. And in particular, what that means is that there exists some more tests that are not part of the developer-written test suite that would, in fact, fail. And of course, again, the developers did not know which of these suggestions they're getting. They're just getting a suggestion that makes all the tests pass. We had a participant come in, and we picked one of the 9 defects at random, and then we picked one of the 4 treatments at random. And so then the developer got 30 minutes to try to produce a patch. And then we repeated this with each developer 4 times. So each developer got to do 4 defects picked at random, and they got to do each treatment group once in a randomized order. So what did we find? Well, first and foremost, we looked at how likely were the developers to actually correctly repair the defect. And what we found is that when the developers received no suggestions, so this is a control group, about 37% of the time the developers were able to correctly repair the defect. So this is our baseline. But when they got a correct suggestion, whether it was human written or automatically program generated, that probability of correctly repairing bug went up to 93%. So a huge jump in the likelihood that the developers were actually able to correctly repair the defect. That's great. However, when the developers got to see a deceptive suggestion, so a suggestion that made the test pass but was not actually correct, they only submitted a correct patch 20% of the time. So they were still able to sometimes detect that something is wrong and produce a correct patch, but the probability of them submitting a correct patch went down. So the difference with the improvement with correct suggestions versus no suggestion is statistically significant. This difference with a deceptive suggestion is weakly statistically significant. So the first thing that we see here is that correct code suggestions have a huge positive impact on success. Perhaps not surprising, but the impact of this is really, really big, and much bigger than the impact of the deceptive suggestions. And the second thing we found is that whether code suggestions were human written or automatically generated actually had no statistically significant difference. So this is great. This suggests that automatically generated patches are actually just as good as communicating information as the human written ones. The next thing we looked at is the timing. Does getting a suggestion speed up development? So you can see that the slowest group here is the control group that got no suggestion. And in fact, if you got a deceptive suggestion, statistically you were not different from the control group. It took you just as long on average to try to produce a patch. But if you got a correct suggestion, whether it was developer written or automatically generated, you produced a patch much, much faster. So again, this is great, but the really interesting thing here, I think, is that people took just as long when they got a deceptive suggestion as if they got no suggestion at all. So this suggests that developers are actually able to detect that something is wrong in the deceptive suggestions and then go ahead and they spend just as much time trying to repair the defect. So this is great. This gives us hope that developers are able to tell that something is wrong when they get a deceptive suggestion. And in fact, we asked developers to rate the quality of the suggestions they received. And you can see that on a scale of 0 to 10, when they got the correct automatically generated suggestion, they gave it a very high score, almost 9. Same thing on the right here, the developer-written suggestions, a score of above 8, statistically indistinguishable. And so what we see here is when the developers got a correct patch, they rate them very, very highly. But when they got a deceptive patch, again, they were not told, of course, that the patch is deceptive, you can see that the distribution looks quite different. There's still some participants who rated the suggestion highly, but you can see that that bar at the top is much smaller than for the correct patches, and then there's a large bar down at the bottom and a big chunk of the distribution where the developers are clearly seeing that something is wrong with these patches. So this is great. This suggests that developers have some intuition, or at least often have some intuition, that the deceptive code suggestions are wrong. And if we can just build tools to empower the developers to trust that intuition and to go ahead and not submit those deceptive patches, we can perhaps reduce this risk, reduce the negative effects of overfitting and automatic program repair. So we conclude three things. First, overfitting in automatic program repair is a serious problem. It poses a serious risk to its effectiveness, even when being used with humans. So one of the most important things that automatic program repair research can be focusing on is trying to reduce overfitting and improving the quality of the patches that we're generating. However, there's hope that humans can help with this process. So developers were often able to detect deceptive code suggestions, and they actually had this intuition that the deceptive code suggestions were wrong. And so if we can build tools to empower developers to build on that intuition, we can perhaps reduce some of the risks. Ultimately, we found that automatic program repair benefits seem to outweigh the risk of deceptive suggestions, right? That benefit of getting a correct suggestion was much greater. Now, of course, it depends on the domain and it depends the specific risks of that domain, but overall the benefits seem to be great. And there's really great hope for automatic program repair being used as part of this manual human-driven repair process. Now, I've told you about just a few experiments from our paper and just a few of the findings. If you find this interesting, I encourage you to go and read our full paper. And we have a replication package that allows you to replicate all experiments, and all of our data is made public. Thank you very much.